All right, today we are diving into one of the most powerful tools in all of science, hypothesis testing. This is the framework, the actual step-by-step process we use to cut through all the noise and figure out if a new idea is the real deal or if what we're seeing is just a random fluke. So let's jump right in.
So let's say you've got a brilliant idea. Maybe it's a new teaching method, a groundbreaking drug, or even just a new marketing slogan. You're convinced it's better than what everyone else is doing. But how do you actually prove it? How do you go from a gut feeling to rock-solid evidence? Well, that is the big question we are tackling today.
And the answer to that question is a formal, structured procedure called hypothesis testing. You can think of it as the engine of scientific discovery. It's a system that lets us use data to test our predictions and hopefully make some objective conclusions about how the world works.
Okay, so at the very heart of every single hypothesis test, there's a conflict. It's basically a showdown between two competing stories, two possibilities. Let's meet our two main characters.
So on one side, you have the null hypothesis, which we call H0. Think of this as the default position, the status quo. It's the boring reality where your new idea does nothing. There's no effect, no difference, no relationship. Then, on the other side, you've got the alternative hypothesis, HA. This is your big idea. This is the exciting new possibility you're testing, the claim that there is a real effect out there that needs to be proven.
Now, the logic here is super important, so stick with me. We don't actually try to prove our new idea is true. Instead, what we do is we try to prove that the null hypothesis is false. The best analogy is a courtroom. The null hypothesis is innocent until proven guilty. We're the prosecution, and our data is the evidence we're presenting to the jury to try and overturn that innocent verdict.
We also have to decide what kind of difference we're even looking for. A two-tailed test is kind of like casting a wide net. We're just asking, is there any difference here? For example, maybe a new fertilizer makes plants grow taller, or maybe it makes them shorter. We're open to either. A one-tailed test, on the other hand, is way more specific. We use that when we have a strong reason to predict the direction, like we're testing a new drug that we believe can only be better than the old one, not worse.
Okay, so we've got our two competing hypotheses lined up. But here's the thing. Before we even peek at a single data point, we have to set the rules of the game. We have to decide ahead of time what's going to count as convincing evidence.
So when we make our final decision, there are really only 4 things that can happen. 2 of them are great. We make the right call. But there are also 2 ways we can get it wrong. A type 1 error is a false positive. We shout eureka and say there's an effect when there actually isn't one. And a type 2 error is a false negative. We miss something that's really there, which is a huge missed opportunity.
So this is absolutely crucial. We have to decide before we even start how much risk we're willing to take of making that type 1 error, that false positive. This risk level has a name. It's called the significance level, or alpha. It's our line in the sand, our standard of proof.
And by far, the most common alpha level you will see everywhere in research is 0.05, or 5%. What this means is that we, as the researchers, are willing to accept a 5% chance of being wrong and concluding there's an effect when, in reality, there's nothing going on. This basically sets a 95% confidence level for our test.
All right, the rules are set. The stage is prepared. Now it's time for the main event. We go out, we collect our data, we run the numbers, and we see what the evidence says. It is time for the verdict.
Now, the star witness in this trial is something called the p-value. And honestly, it's one of the most misunderstood concepts in all of statistics. All it really does is answer one very specific question. Assuming the null hypothesis is true, that our idea has no effect, what's the probability of seeing the results we just saw? So a teeny tiny p-value means our results would be incredibly surprising, like a 1 in a million shot if there were truly no effect. And that makes us start to doubt our initial assumption.
And the decision rule? It's actually beautiful in its simplicity. We just compare our evidence, the p-value, to our preset standard of proof, alpha. If the p-value is smaller than our alpha, we say the result is statistically significant. The evidence is strong enough, so we reject the null hypothesis. But if the p-value is greater than alpha, the evidence just isn't strong enough. We don't have what it takes to overturn the verdict, so we fail to reject the null.
So we have our verdict. Awesome. But what if we made a mistake? I mean, what if there really was an effect, but our test just wasn't sensitive enough to pick it up? This brings us to another really important piece of the puzzle.
And that piece is called statistical power. The best way to think about it is like the magnification on a microscope. Power is just the probability that your test will correctly spot a real effect if one is actually out there. You want a powerful test. Most of the time, researchers are aiming for a power of 80% or higher, which means they have an 80% chance of finding a true effect.
So where does this power come from? Well, it's a mix of a few things. For instance, a really big, obvious effect, what we call a large effect size, is just easier to spot. Makes sense, right? Also, having more data, like a bigger sample size, almost always boosts your power because it helps reduce random error. And finally, if your data is really clean and has less random noise, the true signal is just going to be easier to hear. We are almost at the end of this journey, but there's one last, absolutely critical distinction we need to make. Just because a result is statistically significant, does that automatically mean it's actually important in the real world?
And the answer is a big, resounding no. When it comes to looking at results, it turns out that size really, really matters. This is the huge difference between finding an effect and that effect being big enough to care about.
Think about it like this. Statistical significance just answers the question, is there a real effect here, or is this probably just random chance? But practical significance asks the so what question. It asks, okay, the effect is real, but is it big enough to actually matter to anyone?
And this is a super important takeaway. If you have a study with a massive sample size, your test can become so powerful, so sensitive, that it can detect effects that are technically real but are so tiny they're completely trivial. I mean, imagine a new diet pill is statistically proven to help people lose weight, but the average weight loss after a whole year is just half a pound. Sure, the effect is real, but is it practically significant? No way.
So we'll leave you with this final thought. The next time you see a headline screaming about a significant new finding, be a little skeptical, be a critical thinker. Look beyond that p-value and ask about the size of the effect. Because the question that truly matters isn't just, is it real? It's, is it important?